Children, good morning. Yesterday's topic I am continuing first. Let me complete first chemical bond and periodic classification. Okay? Now, please concentrate and listen. In PO4 3 minus, the formal charge on each oxygen atom and the PO bond order respectively. Whenever such compound is given, first you need to focus your attention. PO4 3 minus means how many charges are there? Negative charges 3. So, 3 oxygens will carry negative charge and 1 oxygen will get a double bond. So, if you take this compound, formal charge, here formal charge in the sense we will not use that normal formal charge formula, here we can use this method also. Total number of charges 3, 3 negative charges shared by 4 oxygen atoms. So, it becomes minus 3 by 4. And the next thing is PO bond order up to 20 electrons species we use molecular orbital theory, above 20 electrons we follow this method. Number of bonds between identical atoms, so phosphorus and oxygen all are PO bonds only. So, total number of bonds, bond order is equal to number of bonds between identical atoms 1, 2, 3, 4, 5 by total number of resonating structures. For this molecule we get each time 1 oxygen will carry this double bond. So, total 4, answer is 1.25. So, formal charge is minus 3 by 4 and bond order is expected to be 1.25. Next one, molecule with least bond angle. Now, if you compare this bond angles, least bond angle means we decide the bond angle based on hybridization. And of course, dipole moment also explains, helps in deciding the bond angle. For example, if you take methane sp3 hybridization, so approximately 109 degrees 28 minutes. And now this is water is 104 degrees 31 minutes. Ammonia 107 degrees approximately 28. H2S, in H2S there is no hybridization. H2S direct overlap of orbitals takes place. Whenever direct overlap of orbitals take place, the bond angle is expected to be nearly 90. So, round about 90, 91. So, approximately 92 degrees is expected for H2S. Remaining all sp3 hybridization because of one lone pair slight deviation in bond angle, 2 lone pairs more deviation, no lone pairs no deviation, tetrahedral bond angle 109 degrees 28 minutes. But in H2S, see in hydrides except ammonia, remaining hydrides no hybridization, except water in other hydrides no hybridization. When hybridization is not present, we can take direct overlap of atomic orbitals. As per VBT, whenever direct overlap of orbital take place, angle is expected 90 degrees because the two p orbitals are perpendicular to each other. So, expected angle is 90 degrees. This is in water molecule. As per VBT, in water bond angle is 90. So, whenever direct overlap of orbitals is considered, bond angle is expected to be approximately 90. Next, the sequence, one more point children, listen carefully, this is very much important, helpful to you. For example, if you take NH3, PH3, ASH3, SBH3, BiH3, because many students ask several times this question. Only in ammonia hybridization takes place, so bond angle is expected to be around 107 degrees. Now, in remaining hydrides, bond angle is nearly 90, means 92, 91, 90, 90 like that. Suppose if you take this ammonia, the central atom, hydrogens are same everywhere. If you take the central atom, as the electronegativity of the central atom decreases, electronegativity of the central atom decreases, bond angle decreases. Remember children, as the electronegativity of the central atom decreases, bonded atoms are same, central atom electronegativity decreases, bond angle decreases. So, around 90 they have. Next one, suppose if you take NF3, NCl3, NBr3, Ni3. Now look at all these examples. Here central atom is same, but bonded atoms are different. Central atom same. In the previous case, bonded atom same, central atom different. Here bonded atoms are different, central atom is same. So when central atom is same, as the electronegativity of the bonded atoms decreases, see from fluorine to iodine, electronegativity decreases, bond angle increases. Bond angle increases with decrease in electronegativity of bonded atoms. Bond angle increases with decrease in electronegativity of bonded atoms. Next. The sequence of energy levels of molecular orbitals for lithium, beryllium, boron, carbon, nitrogen. If 2s and 2p mixing is allowed, all of you please remember, up to nitrogen 2s and 2p orbital mixing takes place. Whenever 2s 2p mixing takes place, we follow the order sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2, sigma 2pz2. After that pi star 2px, pi star 2py, sigma star 2pz. This is the order to be followed up to nitrogen for 2s 2p mixing takes place. If 2s 2p mixing is not possible in the given examples, then what we do is we follow the above 14 rule. Above 14 rule is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2 is equal to pi 2py2, pi star 2px is equals to pi star 2py greater than sigma 2pz, sigma star 2pz2. This is the order for above 14 electron species, means from oxygen onwards we follow this rule. Below 14 we follow this rule, above 14 we follow this rule. But for these elements, if 2s 2p mixing is not possible, then we follow below 14 ki we follow above 14 rule if s and p mixing does not occur. Now we can take one example, and bond order can be calculated by using the formula number of electrons in bonding molecular orbitals minus number of electrons in anti-bonding molecular orbitals by 2. Next, which of the following, for example, all of you look, whenever 14 electrons are given, 14 electrons means N2, CO, NO plus Cn minus. Look at this, 6 plus 8 14, 7 plus 8 15 minus 1 14, 6 plus 7 13 minus 1 14. All these are isoelectronic species. For all isoelectronic species, bond order is expected to be same as that of nitrogen. So, for example, N2 molecule 1s2, sigma 1s2, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. After that pi 2px2 is equal to pi 2py2, sigma 2pz2, 2, 4, 6, 8, 10, 12, 14. Now here bonding orbitals means without stars, 2, 4, 6, 8, 10 minus anti-bonding stars 4 by 2, 3. So bond order is expected to be 3. Here bond order is 3. For all these species bond order is expected to be 3. And one more thing, you see 14 electrons are there, bond order this is for example nitrogen, bond order is 3. If 15 electrons are there, 2.5. For example, O2 plus, O2 is 16 electrons plus 1 electron is removed. So, 2 O2 plus 16 electrons, 2 O2 is the example, 17 electrons 1.5 O2 minus, 18 electrons 1 O2 2 minus. Easily we can remember these 14 3 15 2.5 16, just decrease one number. So, bond order is expected to be O2 2 minus. This is called peroxide, this is superoxide. You know KO2, KO2 potassium superoxide, CSO2, this carries plus 1. So, this whole thing carries minus 1, minus 1 for 2 oxygens. So, 1 oxygen it is minus 1 by 2. So, superoxide oxidation state of oxygen is minus 1 by 2. So, this is about bond orders. Now, here see the question, which of the following species have the same bond order? Bond order is expected to be same for. Now, look at this option NO plus and CO minus. I gave this already, NO plus Cn minus, because they are isoelectronic species. In which pair the stronger bond is found? In the first species. Stronger bond is found in the first species means higher the bond order, greater is the stability. So, more bond order, more is the stronger bond. For example, if you see O2 minus, O2 minus ki just now I gave 1.5, this is 2, N2 3, N2 plus 2.5, NO plus means nitrogen 7 plus 8, 15 minus 1, 14 electrons. 14 electrons means bond order is 3. Here 7 plus 8, 15 plus 1, 16, bond order is 2. Just you remember this, this will help you a lot. 14 ki bond order 3, 15, 2.5, 16, 2, 17, 1.5, 18, 1 bond order. Easily we can just count these two, 7 plus 8 atomic numbers, 15 plus 1 minus charge is there, add 1. So, 16 electrons, 16 electrons bond order is 2. So, wherever bond order is greater, in this case first one is greater bond order than second. In this case first one is greater bond order than second. Here first one is having less bond order. So, is asking stronger bond means higher bond order, B and C. So, answer is B and C, fourth option. Next, the molecular orbital shown in the diagram can be described as, this is one orbital. How this bond formation takes place, I will explain. For example, if you take 2px2 or 2py2, 2px2, 2py2. Now, here subtraction of wave functions, this results in the formation of a bond like this, positive, negative, negative, positive. This leads to see, this is nodal plane, this is nodal plane. Maximum number of nodal planes 1, 2, 2 nodal planes are expected for this. Maximum number of nodal planes are expected for pi star 2px2, pi star 2px2 or pi star 2py2. This is pi star 2px2, 2py2, pi orbitals with stars have maximum 2 nodal planes. Rest all of them have 1 nodal plane. Next, stability of the species Li2, Li2 minus, Li2 plus. Lithium, total number of electrons are expected to be 6, 3 plus 3. So, sigma 1s2, sigma star 1s2, sigma 2s2. If you take this, bond order is number of bonding orbitals 2 plus 2, 4, minus 2 by 2, this is equal to 1. So, in Li2 bond order is 1. Now, coming to Li2 minus, Li2 minus means 7 electrons. 7 electron means next electron sigma star 2s1, sigma star 2s1. So, if you take this, now bonding orbitals are 4 only, anti-bonding orbitals 3, 2 plus 1, 3. So, 1 minus 1 by 2 is equal to half. So, bond order is expected to be Li minus ki half. Li2 plus is nothing but 1s2 5 electrons, sigma star 1s2, sigma 2s1. Now, if you take 5 electrons, 3 minus 2 by 1, 3 minus 2 by 2, that is 1 by 2, 0.5. So, for Li2 minus and Li2 plus bond orders are expected to be same. But how to decide? Li2 means here if you see the options, Li2 minus is less than, Li2 plus less than. Actually expected is Li2 greater than, Li2 plus is equal to Li2 minus as per the bond orders 0.5, 0.5 same, but he gave this option. Why it is so? Increasing order. Why this one Li2 minus is less, though bond order is same, the stability is less for Li2 minus because electron is entering into anti-bonding orbital. Whenever electron goes to anti-bonding orbital, bond order will be less, I mean stability will be less for that. Next, which of the following cannot involved in hydrogen bonding? Cannot be involved in hydrogen bonding. Hydrogen bonding condition is hydrogen atom with more electronegative atoms like nitrogen, oxygen, fluorine. Only with these 3 elements hydrogen bond formation takes place. And the difference in actually it is a weak electrostatic force of attraction between hydrogen atom and the most only these 3 electronegative atoms. Now, sometimes they will ask you a question, strongest hydrogen bonding among the given, then he will give FH, F, OH. Whenever hydrogen comes between 2 highly electronegative atoms, the bond formed is considered to be hydrogen bond. Now, look at this, if you take fluorine, when hydrogen comes between, for example, if you take HF molecule, 1 HF, second HF, third HF. So, it is not linear as we expect, it is somewhat angular. Bond angle is expected to be 120 degrees. This is the last paragraph in NCERT textbook in chemical bond chapter. So, angle, whenever hydrogen bond is there, angle is expected between 100 to 140 degrees. In HF it is 120 degrees. See, whenever hydrogen sandwiched between 2 highly electronegative atoms like 2 fluorine atoms, then the bond formed is hydrogen bond. Here also same, 2 fluorines, 2 oxygens, 1 fluorine, 1 oxygen. So, strongest means first fluorine, after that third one comes, because here oxygen, when compared to oxygen, is fluorine is more electronegative. So, greater the difference, small size and high electronegativity, small size, high electronegativity. These are the 2 conditions required for hydrogen bond formation for combining atoms. Combining atoms means nitrogen, oxygen, fluorine. So, first, after that third one, then second one. Next, which of the following is involved in hydrogen bonding means metanitrophenol, salicylaldehyde, DNA. DNA you know very well that 2 strands are held together with the help of hydrogen bonding. Salicylaldehyde, salicylaldehyde is nothing but orthohydroxybenzaldehyde. This is benzaldehyde, orthohydroxy OH. Whenever hydrogen comes between 2 highly electronegative atoms, the bond formed is hydrogen bonding. Salicylaldehyde, salicylic acid. Next, orthonitrophenol or metanitrophenol. You see this phenol OH nitro group N double bond O. Suppose if you take this, here we can see the hydrogen. This is called intramolecular within the different groups of the same molecule. This is also intramolecular. Such intramolecular bonds are called chelating hydrogen bonds. Next one, meta only in ortho we can see the intramolecular. Para or meta if you take paranitrophenol or metanitrophenol, as the distance between these two is more, we cannot expect intra, but it can form another hydrogen bonding with the HF or some other molecule. See, whenever hydrogen comes between two highly electronegative atoms, we can see the hydrogen bond formation here. So, except ortho, para and meta form intermolecular. Next one, the type of bonds present in copper sulphate 5H2O. This is copper sulphate 5H2O. CuSO4 5H2O structure is copper, and day 2 secondary valencies are satisfied by 4 water molecules, and sulphate is the anion. It forms one hydrogen bond with water molecule. Now look at this. What are the different types of bonds present between copper and sulphate? Ionic bond is present. In water molecule, only in water we can see covalent bond. Between these two, metal and ligand, a day 2 bond is present. Not one day 2 bond, day 2 bond, how many donors are there? Those many day 2 bonds. Next one, outside sulphate, anion and water, one water molecule we have written, here hydrogen bond is expected. So, this is the best example which contains ionic covalent day 2 hydrogen bonds. In yesterday's class, some people asked NH4Cl, how it is an example for ionic covalent and day 2. NH4Cl is nothing but NH4 plus Cl minus, ionic bond is present between these two. Ammonia, in ammonia there is a covalent bond. Ammonia with proton H plus means no electron, so a day 2 bond is expected. In ammonia we can see covalent bond. Only in ammonia covalent is there between ammonia and H plus, a day 2 bond is present between these two ionic. So, NH4Cl is best example for ionic covalent day 2 bonds, but additional hydrogen bond is also expected. Children listen ma, whenever odd number of water molecules are there, MgSO4 dot 7H2O, if you take this one, if odd number of water molecules are present, one hydrogen bond is there. So, for example, if you take CaSO4 dot 2H2O, gypsum, even number of water molecules, whenever 2, 4, 6 water molecules are present, no hydrogen bond is there. Only in odd water molecule containing compounds, one bond is hydrogen bond. Next, which of the following hydrogen bonds is relatively stronger? Few minutes back I explained, where the difference in electronegativity is more, that bond is expected to be stronger. So, answer is F. I gave another example, OHO, FHO. If you take, this is much stronger when compared to that one. Next, the types of bonds present in KHF2. KHF2 means K plus HF2 minus. This is the one. K plus HF2 minus. Ionic is there between these two. In HF, only HF, though electronegativity difference here 4, this is 2.1, the difference is 1.9, but still as though it is greater than 1.7, it is not ionic, it is covalent. Only in HF covalent is there. HF2 minus, there is a hydrogen bond. So, we have ionic is there, covalent bond is there, hydrogen bond, all 3 types of bonds are present in this molecule. Next, intramolecular hydrogen bonding is absent in. Intramolecular is absent in. Intra means only ortho substituents. Orthonitrophenol, of course it is there. Orthofluorophenol, because nitrogen, fluorine can form hydrogen. Salicylaldehyde, which I showed in the previous example. Orthonitrobenzaldehyde. Children, listen carefully ma. Orthonitrobenzaldehyde means C double bond O H. Now, if you take this molecule, this is orthonitrobenzaldehyde. Whenever hydrogen comes between two highly electronegative atoms, the bond formed is hydrogen bonding. Here there is a possibility to form hydrogen bond because this is the most electronegative oxygen, but you see this carbon. Carbon is not sufficiently electronegative atom because only 3 electronegative atoms like nitrogen, oxygen, fluorine are considered. Carbon is not there in this list. Small size high electronegativity list, carbon not there. That is why in orthonitrobenzaldehyde there is no hydrogen bonding. HCl, hydrochloric acid, H2S, in this molecule, though chlorine and sulfur are sufficiently electronegative, because of their large size, there is no hydrogen bonding in these molecules. In our textbook, there is a possibility to form hydrogen bonding in HCl given, but actually we will not consider hydrogen bond in hydrochloric acid. Only chloral hydrate, CCl3 CHOH taken twice, CCl3 CHOH taken twice. In this molecule, hydrogen bond is seen between hydrogen and chlorine. Rest no other compounds of chlorine hydrogen bond is expected. This is chloral hydrate. Next, bond polarity is least in polarity. Greater the difference in electronegativity, more is the polarity. And we have to see the difference in electronegativities. NH, nitrogen is 3, this is 2.1. OH, 3.5 and 2.1. Hydrogen is 2.1, fluorine is 4. Carbon is 2.5, hydrogen is 2.1. Now, see the same common atom 2.1, 2.1, 2.1, 2.1. Other atoms, where highest electronegative atom? Fluor. So, fluorine HF followed by OH followed by NH3 followed by CH. In CH, there is less difference in electronegativity. So, least polar is CH bond. This molecule has dipole moment x dpi. Which of the following other molecule also has the dipole moment x is asking. One molecule, this dipole moment he has given. Which other molecule in the given 4 examples will have same dipole moment he is asking. For example, 135 trifluorobenzene. 135 trifluorobenzene means this one. It is symmetrical in nature. Whenever symmetrical structure is there like this, or when two fluoro groups are para to each other, their dipole moments will get cancelled. Symmetrical molecules melting point high, dipole moment is 0 when identical groups like this are present. If these two groups are not identical, though they are para to each other, their dipole moments are not equals to 0. So, this is molecule having 0 dipole moment. 1, 2, 3, 5 tetrafluorobenzene. 1, 2, already 1, 3, 5 I wrote. 1, 2, 3, 5. Now, if you take this one, just now what I told, for this molecule, dipole moment is expected to be 0, right. So, after cancelling all these bond moments, now only this single fluorine atom is left out. So, the structure becomes one fluoro compound after cancelling these moments. So, this one and this one are the same. So, the dipole moments are considered to be identical. So, this molecule is having same. Next one. Dipole moment of Hx, even sorry children, listen. One more example. If they give some compound like this 1, 2, 4, even for this molecule, these two are para to each other. So, their bond moments will act in opposite direction. So, they will get cancelled. Now, the resultant bond moment is only because of this molecule. This is nothing but fluorobenzene only. Even this is also having same dipole moment as that of fluorobenzene. Next, the dipole moment of Hx is given. If the percentage ionic character of the bond is also given, then its bond length is asking. You know, percentage ionic character is equals to mu observed by mu calculated into 100. This is the formula. He gave percentage 25, mu observed 1.2D అంటే 1.2 into 10 power minus 18 ESU centimeter. 1 dBi is equals to unit of dipole moment. ESU 10 power minus 18 ESU centimeter, 10 power minus 18. So, 1.2 into 10 power minus 18 by mu calculated into 100. This if you simplify, mu calculated is equals to 1.2 into 10 power minus 18 by 25 into 100. 1s are 4s are. So, 4.8 into 10 power minus 18, 10 power minus 18. This is dipole mu calculated value ESU centimeter. Now, you know the formula, mu is equals to delta into L. Delta is the charge, L is the length. See the question, bond length is asking, this one. Charge, mu is what we got, 4.8 into 10 power minus 18, and you know charge is 4.8 into 10 power minus 10 ESU. Length we have to find out. So, length is equals to 10 power minus 18 centimeters or 10 power minus 10 meters. So, now see the answer, minus 8 centimeters not there. So, 10 power minus 10 meters. Next, which of the following would have a permanent dipole moment? What is the meaning of permanent dipole moment? Means which compound possesses dipole moment, that is nothing but permanent one, remaining no. BF3, BF3 is trigonal planar structure. Here this is the molecule. As it has trigonal planar structure, listen carefully ma, all linear molecules with sp hybridization, all trigonal planar molecules with sp2 hybridization and all tetrahedral symmetrical molecules with sp3 hybridization expected to have 0 linear, for example CO2, HgCl2, C2, CS2. Next, trigonal planar BF3, BCl3, SO3, all these have 0 dipole moment. Tetrahedral molecules CH4, SIF4, CH4, SIF4, CCl4, these all are expected to have 0 dipole moment. So, which molecules have dipole moment? For non-linear, neither linear, non-angular, angular molecules, non-linear molecules or angular molecules other than these have dipole moment. For example, if you take BF3 trigonal planar, dipole moment 0, SIF4 tetrahedral, sp3 hybridization, it has 0 dipole moment, it has 0 dipole moment because all bond polarities will get cancelled. SF4, XCF4, you just have a look at this. XCF4 does not come under any of these 3 lists, but under XCF, suppose if you take XCF2, here molecule has square planar structure. Actually geometry is octahedral with square planar because 2 lone pairs occupy axial positions. The molecule is considered to have square planar structure, planarity is there. So, that is why its dipole moment is 0. See, even XCF2 hybridization is sp3d, this hybridization is sp3d2, but still this has 0 dipole moment. XCF2 has linear structure, both bond polarities will get cancelled, and these lone pairs are in a trigonal planar model. So, its dipole moment is 0. So, now SF4 molecule, you know SF4 has seesaw geometry, seesaw. Now, this molecule has permanent dipole moment, rest all of them have 0. Next. Student, now I am going to start periodic classification questions. Next, please follow and listen carefully. The places that were left empty by Mendeleev for which elements? He left some gaps for those elements which were not discovered at that time. So, for which elements he left gaps? You know, Eka, boron, scandium. Eka boron was the one element, he left that place for scandium. Eka silicon, Eka aluminum is gallium. Eka silicon, this is nothing but germanium. So, in the given options, you see gallium, this is nothing but Eka aluminum, germanium is Eka silicon. So, these two places were left. Next, which is not anomalous pair of elements in the Mendeleev's periodic table? Anomalous pairs. Please all of you learn argon, cobalt, already it is there, argon, potassium, argon and potassium. Argon atomic weight is 40, potassium is 39, anomalous in arranging atomic weights. Actually, first element atomic weight should be less than second, but here argon is greater than potassium. Cobalt, nickel 59, 58. Tellurium and iodine 128, 127. And aluminum, silicon, these are not anomalous pairs. So, learn this. Next, the correct order of filling up of subshells in 7th period. Correct order of filling up of subshells means 6th period 6s, 4f, 5d, 6p. 7th period it becomes 7s, 5f, n minus 2f, n minus 1d, np. So, this is the correct order 7s, 5f, 6d, 7p. This is the configuration. Next, the noble gas in the 7th period of modern periodic table has the symbol. The noble gas in 7th period is last element 118, nothing but organeson. He is asking symbol means octium, UUO, octium. Last 2 years 22, 21, these 2 years they asked this question. Next, this model question. Where would you locate the element with atomic number 114 in periodic table? All of you listen, 114. After 110, the remaining almost all elements, last 2 digits equal to group number. So, 114 means 14th group, group number 14, 13 no, 14, 14. Next, which 114 means after last element 86 radon, 118. 118 means all these belongs to the 7th period. 7th period starts from 113. 113 to 118 belongs to 7th period. So, it is 7th period, and as it is last noble gas element, but it is p block element, p block in group 14. So, 118, 117, 116, 115, 114. 114 means group 14th p block, because p block starts from 113, ends with 118, and all from 110 to 118 all belongs to 7th period only. Next, identify the incorrect match. This is also previous NEET question. Nil anium 101, Mendelevium, MD, correct. Nil tram 103, Laurentium, correct. Nil hexium 106, Seaborgium. Anium anium means 111, that is nothing but rhonginium Rg, but he gave dermstadium, so it is not correct, rhonginium. So, option this last one D4 is wrong. Next, IUPAC symbol of an element is UBN, the element belongs to, you see, on Bm by nilium 120, on by nilium, last it ends with em, on by nilium is 120th element. Suddenly if they ask which period and which group it belongs, means what you do is you see the nearest noble gas 118. 118 is oganesson, we know this belongs to the 18th group in the periodic table and 7th period. After oganesson, next element 119 belongs to group 1. 120, 119 belongs to group S block, 120 also belongs to S block second group. So, it should be second group 8th period, second group 8th period element. Other method is also there, 120 is given. You have to remove 32 because elements differ in their atomic numbers by 8, 18, 18, 32. If more than 100 are there, 2 times 32 comes. So, 32 if you remove 8, again remove 32, we get 56, remove 18, 38, remove 18, 20, remove 8, 12, again remove 8, 4. Fourth is nothing but beryllium. Beryllium configuration 2s2, 1s2, 2s2. So, it belongs to number of electrons, NLX notation, X indicates number of electrons, N indicates the period number, second period, second group. So, this becomes third 3s2, third period, fourth period, fifth period, sixth period, seventh period, eighth period. This method is also there. Different species of iodine can be placed in the increasing order. These are all same atom with a different number of electrons. So, order is anion greater than neutral atom, greater than cation, anion, neutral atom, cation, because anion size is always bigger, but he is asking increasing order. So, you should start from cation, cation, neutral atom, anion. Okay. Next one, screening constant value sigma for the 3s electron of sodium. Screening constant means, look at this, nth shell orbitals will provide 0.35, n minus 1 shell will provide 0.85, n minus 2 and inner shells will provide 1. This is for normal species. For D block we use different. Now, for example, sodium metal given. Sodium is 1s2, 2s2, 2p6, 3s1. This is the electronic configuration for sodium. This is the last shell electron. For this we are providing screening. So, that screening is provided by all these shells which are present inner. This is nth shell. We do not have any other electron in nth shell to provide. So, this we will not consider here. This is n minus 3, 3 minus 1, 2, n minus 1 shell. In n minus 1, 8 electrons are there. These 8 electrons will provide, n minus 1 shall provide 0.85. This is equals to 6.4, 17, 2, 0.85, 17, 17, 4, 6.8. Next, in inner n minus 2, n minus 2 means this one, n not only n minus 2, if inner are there, they are also, in this case it is not possible, 2 electrons, n minus 2 will provide 1, this is equal to 2. So, 8.8. He is asking screening constant. Children, look here, sigma star is asking. If it is Z effective, that is equals to atomic number minus sigma star. Here atomic number of sodium is 11, screening constant what we got is 8.8. So, answer is 2.2. So, Z effective is 2.2. See the question, he is not asking Z effective, he is asking screening constant. So, we should tell this one only. Next, if they ask Z effective, follow this. Effective nuclear charge by a 3d electron of nickel atom. Nickel configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d8, 4s2. Here I am violating the rule. Actually, after 4s2, 3d8 comes, but we are taking shells as per the n value, first shell, second shell, third shell, fourth shell. So, for our convenience sake, I wrote like this. This is nth shell. You know, he is asking d electron, 3d electron. The last d electron is 8th d electron. We are providing screening for 8th d. How many other d electrons are there? Other than 8, 7 are there. So, remaining d electrons will provide 0.35 screening. Remaining 8th d electron ki we are providing screening. Remaining 7 d electrons will provide 7 into 0.35, and all inner for up to 30 elements, always this number is 18 only, take it for granted. So, 18 electrons into 1. So, now this if you simplify, 35, 21, 24, so 2.45, and this is 18. Answer is 20.45. This is nothing but sigma star, screening constant, but is asking what? Effective nuclear charge. So, Z minus sigma star. Atomic number of nickel is 28, minus sigma star is 20.45. So, answer will be 7.55. See the answer? Fourth option. Next. So, children remember, last d electron ki remaining all other d electrons will provide 0.35, and all inner shell electrons will provide 1. Only for 1s 1 electron, this 1s1 electron provide 0.30 screening. For example, if they ask helium, helium configuration 1s2. So, 2 electrons are present, we are providing screening for the second electron, then 1s1, 1s1 electron screening is that 0.3. So, 1 into 0.30, this is 0.30, atomic number of helium is 2, 2 minus 0.3, answer is 1.7. This is an exceptional case. Next. Which of the following arrangements represent the increasing order, smallest to increasing order of ionic radii? You know, isoelectronic species with increase in negative ions, brackets anion, size increases. With increase in negative charge, anion size increases. With increase in positive charge, that is for cations, size decreases in isoelectronic species. Now, you see here nitrogen, oxygen, phosphorus, sulfur, 4 species, 4 elements are given. So, as we move across a period, size decreases. So, nitrogen size is greater than oxygen, phosphorus is greater than sulfur. Okay. Now, next one, you see down the group size increases, across a period size decreases, down the group size increases. So, largest size is expected to be for phosphorus, P3 minus greater than S2 minus greater than N3 minus greater than O2 minus. He is asking what order? Increasing order. So, from less to high we have to see reverse order, O2 minus, N3 minus, S2 minus, P3 minus. So, first option. Ionic radii of N3 minus, same question, but values are given. You know N3 minus greater than O2 minus greater than F minus. So, among the given 4, N3 minus, O2 minus, F minus. So, option 3 is the correct one. Next, crystal radius of one lithium is given, he is asking covalent radius. You know the order, van der Waals is greater than, van der Waals radius greater than, crystal radius greater than covalent radius. Other name for crystal is metallic. Now look at this, he has given crystal radius is 123. So, just relative comparison, van der Waals should be greater than 123 pm picometers and covalent is less than 123. No need to take 40% van der Waals is greater than, no need to calculate, just relative comparison we can give. Next, one more one question. For example, Br minus is radius x angstroms, Br minus covalent radius is covalent radius of bromine, not Br minus, just we will take bromine. Look at this, covalent radius for bromine he has given some x angstroms. What is its atomic radius? You know covalent radius is the other name for non-metal atoms, this is a non-metal, so x angstroms only. Next, the correct order of atomic radii in group 13 elements, this is very important one. Group 13 boron, boron to aluminum size increases, aluminum to gallium decreases, from gallium to indium, indium to thallium. This is boron, aluminum, gallium, indium, thallium. Everywhere atomic radius increases down the group. Only in 13th group we can see this variation. So, aluminum radius is greater than gallium. Why it is so? Because in gallium electrons first time entering into 3D subshell. So, these d electrons cannot provide proper shielding, because of poor shielding effect its size is less. Again from indium to thallium expected increase in size is not observed, because electrons are entering first time in this case, that F electrons are entering, that is why size difference is less here and less here between these two. Next, the smallest size among the following. Smallest size among the following means just you take out the element, this is lithium, this is 5 electrons boron, 8 electrons oxygen, 9 electrons fluorine. So, as we move across a period from lithium, beryllium, boron, carbon to fluorine, neon, atomic radius decreases from lithium to fluorine. All of you listen, largest radius in any period is for the first group element. In every period first group element has the largest, least atomic radius is for halogens. In every period lowest atomic radius is for halogens, largest is for lithium. Again from fluorine to neon, when we move size increases, because for neon we will take van der Waals radius. Noble gases have van der Waals radius, halogens have covalent radius. We know van der Waals is greater, that is why it is the order. This is also very famous question, 0.7 to this is 1.60 angstroms. So, he will give you same values different and you have to pick out the sizes. Which of the following is correct order of increasing second ionization energy? Here please all of you, if you have not done this work, first you do. Second period IP1 order, lithium is less than beryllium, greater than boron, less than boron is less than carbon, less than nitrogen, greater than oxygen, oxygen is less than fluorine, less than neon. This is the order to be followed. Lithium less than beryllium, beryllium greater than boron, this is the order. So, here near two places, beryllium, nitrogen. You see beryllium IP is greater than lithium and boron. nitrogen IP is greater than carbon and oxygen. Clear? This is IP1 order. So, they will give these 4 elements. Arrange them in the order of increasing. So, if you take IP value, carbon is less than oxygen, less than nitrogen, nitrogen is less than fluorine. This is the IP1 order for these 4 elements. Clear? IP1 for first to IP1 for these 4 elements. Next one, if you take IP2 order, IP2 order if you consider, now see, lithium is greater than beryllium because it gets neon helium configuration. Beryllium is less than boron, greater than carbon, less than nitrogen, less than oxygen. Oxygen is greater than fluorine, less than neon. This is the order to be followed. Second IP, you see these 4. Now arrange them. Carbon less than nitrogen, less than fluorine, less than oxygen. This is the order to be followed. See the first IP, second IP. IP1 order, IP2 order. Same thing is expected for third period. Third period, if you take sodium, magnesium, aluminum, silicon, they will give you a graph. Sodium to magnesium increases because paired s electrons. Aluminum decreases, again from here silicon increases. This is the graph, expected IP graph for these 4 elements. Next, IP1 and IP2 of an element are 700, 1200 kilojoule per mole. If 1000 kilojoules of energy is supplied to the gaseous atom, 1000 kilojoules is applied, find the ratio of monovalent and divalent cations is asking. For example, magnesium is there, IP2 700 kilojoule, 1000, okay, any element, first IP, for example, if you take IP1, metal loses 1 electron to form M plus electron. Metal is in the gaseous state. Okay. Now, for this process, how much of energy is required? 700, because IP1 is 700 given. Okay. Now, this element is having 1000 kilojoules of energy with it. That element is having 1000 kilojoules. IP1 is 700. So, from 1000 we can easily spend 700. So, amount left is 300 now. For removing the same from same element for second electron. So, for second electron we require 1200 kilojoules. From M plus to take out one more electron we require 1200. But how much energy this is having? Only 300. You know, for 1200 kilojoules we can remove 1 second electron. 1 second electron to remove, we require this energy. Therefore, with 300 kilojoules of energy, how much fraction we can remove? 1/4. 1/4 we can remove. So, it exists in the ratio, monovalent species is 75%, divalent species is only 1/4, 25. So, it is 3:1 ratio. First option is the right answer. Same question is there in our material. Next, IP1 of magnesium is 737 kilojoule per mole. The energy required for magnesium to Mg2 plus. Look here, many students did this question wrong when they gave this question, Mg plus electron. So, for removing 1 electron, 737 kilojoules of energy is required. For Mg to become Mg2 plus 2 electrons. All of you see this ma? Here how many electrons we are removing? 2 electrons. It is not +1 to +2, directly 2 electrons. For 2 electrons we require additional energy. Additional energy means first one is this, means second one is double that of this. So, around 1400. So, if you add 737, Just students will tick this answer, but it is not the correct answer. That only for second electron we require approximately 14. Now first and second together 2 electrons are there in this. First electron 737 and second electron like this. We require some 1450. So 737 plus 1450. If you add these two, we get this energy. So here as two processes are there, you have to add IP1 plus IP2. Next. The electron affinity of X minus is equal in magnitude with the ionization potential of electron affinity of X minus. X minus, if you add an electron, it becomes X2 minus. This is electron affinity of X minus. Now what is the reverse process? This is EA, and reverse process is nothing but IP. So IP of X2 minus, from this if you remove an electron we get X minus. If you add electron we are getting this, if you remove an electron we get this one. So this is equal in magnitude to IP of X2 minus. Here children listen, A plus electron, A plus electron gives rise to A minus. A minus, that is electron affinity of A is equal to A minus, IP of A minus is equal to I. This is valid for all except one element. Which element it is not applicable means for chlorine. Chlorine ki IP and electron affinity values are not same, because chlorine is the most highest electron affinity element in the periodic table. Successive ionization energies of these one element are given. These are all IP values of same element. See, 5 IP values are given. He is asking the formula of its bromide. So you compare the values 8.3, 25.1. Always IP successive ionization potential values increases. So IP2 greater, IP3 greater, IP4, IP5. Now when they give values like this, you select the two IP values where the hike is maximum. If you see, this is within the normal range, this is also within the normal range, but you see the difference here 37 point, okay, you take it as 40 and 260, difference is 220 units. If you take the difference between 260 and 340, 260, 340, less difference, 80 units difference. So maximum difference is found between third and fourth. So this metal loses 3 electrons comfortably. For removing fourth electron, it requires such a high energy. So metal valency is to be taken as 3. Where the hike is maximum, that there up to there we can remove electrons. After this, as the difference is very high, it cannot lose. So metal valency is 3. He is asking formula of bromide. Bromine valency is 1. So formula after crisscrossing is MBr3. This is the one, MBr3. Suppose if they ask same question, what is the formula of its phosphate? Metal is 3, phosphate is 3. 3 will get cancelled, MPO4 is the formula. Metal sulfate, if they ask, metal is 3, sulfate is 2. Crisscross, then the formula is M2SO4 taken thrice. This is the one. So these are all formulae. Suppose metal valency is 2, oxygen metal valency 3, same thing will take. Oxygen is 2, crisscross M2O3. What is the molecular weight of this? As we do not know the metal, we will take it as 2m. Oxygen weight 16, 3 is 48. So 2m plus 48 is the molecular weight of its oxide. Order of electron affinity of 6th group elements. 6th A group means 16th group elements, very important. 16th group elements are called chalcogens. Chalcogens electron affinity is the very important order. Always second element in a group has high electron affinity than first element. So we can take sulfur, selenium, tellurium, polonium, oxygen. This is EA1 order, EA1. EA2 order if you take, same order, oxygen, sulfur, selenium, tellurium, polonium. This is EA2 value. Next, A minus gives rise to A plus okay. A minus gives rise to A plus. Now, this is the question given, but we know that A minus cannot be converted directly to A plus. A minus will be first converted into A minus to A becomes A plus. See, look at this ma, A minus to A, direct conversion not possible, A to A plus. This is step 1, this is step 2. For these two, see, because directly A minus to A plus, step together is 600 kilojoules, he gave in the question, 600 kilojoules. IP of A is given, IP of A means this step, second step, A becomes A plus, this is IP. He gave its value as 500 kilojoules. Together is 600, only one step is 500, so this becomes 100. Now, you see the question, then the electron gain enthalpy of A. This is A minus, to become A means IP of A minus. Electron affinity of A means this step, A becoming A minus. If the forward reaction is plus 100, backward reaction becomes minus 100. So, answer is minus 100. This is the answer. Clear? Next. The electronegativity of the following elements increases in the order. Electronegativity increases in the order. Here you should know something. Electronegativity increases across a period. Across a period, electronegativity increases. Down the group decreases. So, here first sort out the elements: carbon, nitrogen, silicon, phosphorus. These two belongs to the second period, these two belongs to the third period, second period, third period elements. Out of these two, nitrogen is greater than carbon. Out of these two, phosphorus is greater than silicon. And down the group, what happens to electronegativity? Decreases. So, if you take the order, we will get carbon order increasing, he is asking which order? Increasing order is asking. Increasing order means highest electronegativity is for nitrogen. So, nitrogen there is only one option. So, silicon, phosphorus is greater than silicon. So, silicon is less than phosphorus, carbon is less than nitrogen. Second period elements have more electronegativity than third period. Next, suppose if they ask electron affinity of same 4 elements. Electron affinity, if they ask, children listen carefully ma. Electron affinity is generally negative, first electron affinity, only for few elements like beryllium, magnesium, nitrogen and noble gases. These elements, all noble gases have positive, first electron affinity is positive. For all these elements positive, you should keep this in mind. So, as we move across, electron affinity increases. As we move down the group, electron affinity decreases, but from second element, not from first. In every group, second element has highest. So, silicon is greater than carbon, phosphorus is greater than nitrogen. This is the order. And as already given, this is the positive enthalpy, electron affinity value is positive for nitrogen. So, nitrogen is having least. So, if they ask increasing order, nitrogen less than phosphorus, phosphorus is less than carbon, less than silicon. This is the electron affinity order for the given 4 elements. If not this, they will give another pair, nitrogen, oxygen, phosphorus, sulfur. Again same trend, electron affinity if they ask, second element is having more than first element. So, out of nitrogen and phosphorus, phosphorus greater than nitrogen, sulfur is greater than oxygen. As we move across, electron affinity increases. So, we can say that as nitrogen is having as it is having stable configuration, it will not accept electron easily. So, we need to give energy to provide an electron to it. So, that is why order, if you take sulfur greater than, oxygen greater than, phosphorus greater than nitrogen. Whenever they ask electron affinity, nitrogen and phosphorus always come at the end, last. Next, among the elements boron, aluminum, magnesium, potassium, the correct increasing order of NCERT textbook question. Order of metallic nature: boron, aluminum, magnesium, potassium. First you do one thing, arrange them group wise, period wise. So, if you take this is second period, third period, fourth period, and you know increasing order of metallic character. Metallic character is more for first group elements. Among all the elements in the periodic table, first group elements are more metallic, and across a period metallic character decreases. So, and down the group electropositivity increases, metallic nature increases. So, we can say potassium is greater than, magnesium greater than, aluminum greater than boron, because down the group metallic nature increases. So, aluminum greater than boron, this is the order to be followed. So, he is asking increasing order. So, boron less than aluminum, less than magnesium, less than potassium. Next, another one, which of the following is most acidic? Most acidic means, here you see magnesium metal oxide, aluminum amphoteric, metal oxides are basic, the other things are metalloids, amphoteric in nature. So, if you take these four, magnesium, sodium, aluminum, calcium, all are metals only, but aluminum is amphoteric in nature. That is why this oxide is having 50% acidic character and 50% basic character. Remaining all are true metals. True metals means metallic nature is there. So, they are all most basic. He is asking most acidic means the one which is having only 50% basic character is more acidic. Others cannot act as acidic. Next, which of the following is an oxide? Very good question. Look at this. Which of the following is an oxide means all looks like oxide only, na? Then how to decide means, if you take cesium peroxide, you take CSO2. You always oxidation state of cesium is +1 only. If this half is +1, the other half is -1. You see, two oxygens are getting -1 charge. So, for one oxygen it is -1/2. -1/2 means it is an example for superoxide. Next one, KO2, same case, this is +1, so it is -1. Two oxygens -1, so one oxygen is -1/2, superoxide. This one you see, barium peroxide. How can we say if it is +2, the other half is -2. So, for two oxygens -2, one oxygen atom -1. Whenever oxygen carries -1 charge, that is an example for peroxide. So, it is a peroxide. First and last are superoxides, second one is peroxide. This is the normal oxide, because silicon is +4, oxygen is -4, two oxygens -4, one oxygen -2. Where oxygen is -2 oxidation, that is an example for normal oxide. Next, the most acidic oxide in second period. Second period, listen, as we move across, non-metallic nature increases, acidic nature increases. So, N2O5 is the most acidic oxide. Please remember it, very important question. In second period, N2O5 is most acidic. Third period, Cl2O7 is the most acidic. Not only in third period, in the entire periodic table, most acidic oxide, stable oxide is this one only. Next, identify the set of oxides contains only amphoteric oxides. Amphoteric is asking. Amphoteric means 50% acidic character, 50% basic. If you take this is not amphoteric, this is not amphoteric. Here all are mixed. This is basic metal oxide, non-metal oxide acidic, non-metal oxide acidic, amphoteric oxide. You see the second option, zinc oxide is basic, beryllium, aluminum, tin, lead, zinc. All these oxides are amphoteric in nature, amphoteric. Now SnO2, ZnO, Al2O3, all are from the list only. Cr2O3. If you take Cr2O3, whenever an element is lowest oxidation state basic, intermediate oxidation state amphoteric, highest oxidation state acidic. So it is in intermediate oxidation state. It can undergo reduction, it can undergo oxidation. So it is an example for, it can act like a amphoteric oxide. Correct order of non-metallic character. Non-metallic, this is also NCERT example. If you take this one, boron, carbon, nitrogen, fluorine, all are from same period, second period. As we move across, what happens to non-metallic nature? Increases. Silicon comes here. Silicon is, as we move down, non-metallic nature decreases. So silicon comes before carbon. But the doubt is, should it come before, after boron or before boron? Second period elements always less non-metallic than, third period are less non-metallic than second period. So answer is silicon less than boron, carbon, nitrogen, fluorine. This is the correct order. Next. Noble gases have the highest ionization enthalpies in their respective periods. Absolutely correct. Noble gases have highest IP because of their stable octet configuration. Stable closed valence shell configuration, both are correct, correct explanation. Successive ionization energies of an element. See, this question already repeated. This is 6th one, this, all these 3 values, and 4th one is 120. We can see the maximum difference between 3 and 4. 3 and 4. So this element loses how many electrons? 3 electrons. So element is A, whose valency is 3, oxygen is 2, crisscross, we get A2O3. This is the answer. Mg plus, look at this, this is first electron affinity, IE1. Mg to Mg2 plus, this is both IP1, IP2 together are present for 2 electrons. Which of the following is correct? IE1 of M plus is 100, we cannot say. See this, IE1 of M plus, this is IE1 of M is given, M plus means this is second IP, so it cannot be the correct one. IE1 of M is 150, that is also not correct. IE of M is 350, absolutely. IE2, only 2 is not 350, plus IE1, IE2 together is 350. Electron gain enthalpy of M plus is minus 100. You see this one, forward is IP, forward direction IP. So backward direction is electron affinity only, na? So electron gain enthalpy of M plus is minus 100, that is the correct one. The element with least negative electron gain enthalpy, least negative electron gain, highest negative value is for fluorine, chlorine minus 349 and fluorine minus 333. Next sulfur minus 200, phosphorus minus 61. So lowest negative value, negative electron gain enthalpy is for phosphorus. This is based on the magnitude. Now list, match the, this model question is expected, very important. Non-metal, most non-metallic, acidic, metal oxide, basic, Al2O3, amphoteric, N2O, neutral oxide, N2O, NO, CO, all of you remember. These 3 are the neutral oxide, N2O, NO, CO. Rest all oxides of nitrogen, N2O3, N2O4, N2O5, these are all expected to be acidic in nature. Remember this list, neutral oxides. considering the elements fluorine, chlorine, oxygen, nitrogen, the correct order of their chemical reactivity in terms of oxidizing nature. Chemical reactivity is decided based on the electrode potentials. So, highest oxidizing nature is for fluorine, and there is a confusion between first and second option. In our material they gave fluorine greater than chlorine than oxygen and nitrogen, but that is not the correct order, this is the correct order. Because electrode potential value is more for oxygen, when SRP values, if you decide oxygen has greater value than chlorine, so option 2 is the correct answer. Which is correct order of reducing character in case of alkali metals? This is also, all of you listen, alkali metals, when metals are given, no water, non-aqueous, it is not mentioned in, if ions are given, ion means compulsorily that is an aqueous state. Here alkali metals is asking. Down the group, what happens to lithium, sodium, potassium, rubidium, cesium? What happens to electropositivity? Increases, metallic nature increases, reducing nature increases, basic nature of oxides, they form basic nature increases, they form basic oxides. See, all these properties increases. Electropositivity, metallic nature, reducing nature, basic nature and basic nature of oxides, all these characters increases. If elements are given, this is the order. So, highest order is for cesium. Cesium greater than rubidium, greater than potassium, sodium, lithium. This is the order to be followed, reducing nature. But if ions are given in aqueous state, listen children, very important, in aqueous state order is not this, we decide based on electrode potentials. As per the SRP values, lithium followed by cesium, but in first group elements rubidium is given in between, after that rubidium, potassium, sodium. So, what is the correct order of reducing nature is, in aqueous state lithium, in normal state cesium. Aqueous is given, this is the order to be followed, normal state is, this is the order to be followed. So, option is correct, option 1 for the right given question. Lithium resembles magnesium due to diagonal relationship, which is attributed to. Diagonal relationship is shown by lithium, beryllium, boron, carbon. Next sodium, magnesium, aluminum, silicon. Now, if you see these two, diagonally related elements have, children, same atomic radii, same polarization power, same electronegativity. So, polarization power is nothing but ionic charge by ionic radius ratio, that is same, sizes are same, Li plus size is similar to Mg2 plus. Polarization power, only ions are to be taken. If they give lithium and magnesium have same Pp polarization power, wrong. Polarization power is considered only for ions. So, Li plus and Mg2 plus have same polarization power. Of course, they have lithium and magnesium elements have same electronegativity. Electronegativity of beryllium 1.5, which other element is having same means aluminum is having same. So, diagonal relationship, same size, same electronegativity, similar polarization power, that is nothing but charge to radius ratio. So, these are some important questions related to periodic table. I have given almost all important questions, please go through this once before exam. Thank you.